All right, we're going to go through the rest of the homework problems. And they are the titration problems, which basically a titration problem has every problem from the chapter in the one problem. All right. Start with 1688. All right. So in 1688, I'm going to add some parts to that titration. All right. We have 0.4 grams of propanoic acid. They should have given the formula for propanoic acid. Molar mass of propanoic acid is 74.08. All right, and we're going to dissolve that to give 50 mils of solution. So the final volume is going to be 50 milliliters of solution. All right, so that's going to be in our Erlenmeyer flask, and we are going to titrate that with a 0.150 molar NaOH. And that will be in our burette. All right, so the problem here just asks for the pH at the equivalence point. So I'm going to add to that. I want the pH initial after 10 mils added at the equivalence point. So initial after 10 mils added at the equivalence point at the half equivalence point. Then I want the after 40 mils added. And then graph. So then you graph it. So this problem just has the equivalence point, but we're going to do the whole titration here. All right, so this is a solid. All right, so a solid, well, it's not a solid, but it has a mass. Actually, propanoic acid is a liquid. But our KHP was a solid. So again, your acid could be a solid that you weigh out. This was a liquid that was weighed out. Just put a beaker on there, tare it, then you add your liquid until it reads 0.400 grams. All right, when you look up propionic acid, you find the Ka, that is 1.3 times 10 to the minus 5. So your Ka is 1.3 times 10 to the minus 5. All right, so A is initial, B is after 10 mils, C is at the equivalence point, D is the half equivalence point, E is after 40 mils added, and then finally F, graph this titration curve. All right, so there's a number of ways you can do the equivalence point, but for the initial, there's only one way to do it. You have A minus and you have HA. So what we're going to have is our HA with our OH minus, which means we're going to need the KB, but initial means before any of the base was added. So no NaOH added. So just in the Erlenmeyer flask. So in the Erlenmeyer flask, we simply have our propionic acid. All right, so I'm just going to say that's HA, generic weak acid, and that gives us H plus and A minus. So initial. So we have to have this in concentration of moles per liter. We have the mass, we have the molar mass, so we can get moles, and then we divide that by our liters of solution. All right, and so to get our initial concentration, we take our 0.4 grams, and we divide by the molar mass, which is 74.08 grams per mole. And so that will give us moles. So when you take your 0.4 divided by 74.08, you get 0.00540. And that is moles, all right? And now we have to divide that by the total volume. And in the problem, it said it made a total of 50 milliliters of solution, which you then convert to liters because molarity is moles per liter. So that is 0.0500 liters. So when you convert 50 mils into liters, 0.0500 liters. Make sure you don't mess up that calculation. So divide by 0.05, and now you have your initial concentration of HA, and that is 0.108 molar. All right, so initial is 0.108 molar. All right, we have 0H plus, 0A minus, so it has to go to the right. All right, so at equilibrium, we have 0.108 minus X, we have X, we have X. And so X squared over 0.108 minus X is equal to, again, you have to always look at the reaction. This is the reaction that we're using. This is the Ka reaction. You use the Ka constant, which is 1.3 times 10 to the minus 5. All right, do we have to check our X value? Well, we take our initial concentration, divide it by the equilibrium constant. And if that's greater than 1,000, then we do not. So we take our 0.108, divide by our 1.3 times 10 to the minus 5, and we get 8,300. All right, so that is greater than 1,000. So our X1 is the final answer. So we can neglect this X. We don't have to do successive approximations. We do not have to do the quadratic equation. We simply take 0.108 times 1.3 times 10 to the minus 5, and then we take the square root of that. That is our X value, and that is our final value for our X. All right, so you get X is equal to 0.00118. All right, and so then, of course, X could be anything. You got to look at equilibrium. What is X? Here's X. X is H plus. Always check to make sure you know what the X is. So now we know that X is H plus. And so the H plus concentration, 0.0018118. And so the pH is the negative log of that. So the negative log of that answer gives us a 2.93. So if we stuck our pH meter in the Erlenmeyer flask, it would read 2.93. We put an acid in there. Of course, it will be less than 7. It will, in this case, be 2.93. All right, so now we're going to add 10 mils of NaOH. All right. So the pH is going to go up. We're adding base. All right, so we're going to add 10 mils of the 0.150 molar NaOH to our 50 mils of 0.108 molar HA. All right, so we have a reaction that has OH minus in it and HA. And there is only one. Again, 3 reactions. Ka, Kb, Kw. They will answer all questions. The only one that has OH minus and HA is Kb. So you have to write the Kb reaction. A minus plus H2O goes to HA plus OH minus. All right, and so initial. So in order to get our concentration, HA is no longer 0.108 because we added 10 mils of the NaOH solution. And so you have to do MV is equal to MV for your HA. You also have to do MV is equal to MV for your OH minus. So HA, it was 0.108 when we put in our 50 mils of our solution. But what is the molarity now that we've added the 10 and our total volume is 60? Your OH minus. We added 0.150 molar when we added the 10 mils. What is the molarity now that the volume is 60? All right, so 0.108 times 50 divided by 60, that is 0.09. Your 0.15 times 10 divided by 60 is 0.025. And then A minus, all right, is 0. All right, so again, anytime you write Ka, Kb, Kw, something on the right must be 0. If it is not, if you have two non-zero numbers on the right, they will react until one of them is 0. All right, and so the smaller number is the one that's going to go to 0. So 0.025 is smaller number. 0.025 plus 0.025. And so our new initial, which has a 0 on the right, has an A minus concentration of 0.0250 molar. And it has an HA of 0.0650 molar and an OH minus concentration of 0. So we have a concentration of HA and A minus and a concentration of any OH or H plus of 0. We have a buffer. And once you see that you have a buffer, you go that pH is equal to the pKa plus the log of A minus over HA. All right, and so the Ka was given. It was a 1.3 times 10 to the minus 5. All right, so since your Ka is 1.3 times 10 to the minus 5, the negative log of that gives you your pKa. So the negative log of 1.3 times 10 to the minus 5 is 4.89. All right, and so our pH is equal to 4.89 plus the log of A minus 0.0250 over HA 0.0650. All right, so log 0.025 divided by 0.065. And that gives you a pH of 4.47. All right. So we had more acid. So again, here is 0.065, more acid, more weak acid, and more of the base. And so looking at your pKa, it's going to be slightly less than the pKa value. And it is 4.77. All right, so now we're going to do the equivalence point. The equivalence point is the hardest question. All right, so I want the pH at the equivalence point. Because in this one and the one prior to that, I gave you the volume. And so you could do MV is equal to MV. When you're doing your titration and going to the equivalence point, you have to calculate the volume required for that equivalence point. And so when you're doing the equivalence point, you have MV over C is equal to MV over C. All right. If my computer ever starts up again. All right. MV over C for your acid is equal to MV over C for your base. All right, so our acid, we know it's 0.108. The volume, we put in the 50 mils. That's in the Erlenmeyer flask. The coefficient is 1. Your base, we use 0.150 molar. The volume, that's what we're looking for. What volume did it require in order to get to the equivalence point? So 0.108 times 50 divided by 0.15, and you get 36 milliliters. And so the volume of your NaOH is 36.0 mils, and then you have your equivalence point. All right, and so now we have to do the same thing that we did before, except we are at the equivalence point, which means that our acid and base have to have the exact same molarity. So still we have our A minus plus H2O goes to our HA plus OH minus. So we're going to do MV is equal to MV. We're going to do MV is equal to MV. And we are at the equivalence point, which means that those two molarities must be equivalent. If they are not, then you have calculated something incorrect. All right, so our acid, 0.108. We use 50 mils. All right, so we now know that it required 36 mils to reach the endpoint. So now our total volume is 86. Our OH minus, the molarity, 0.15. To reach the endpoint, it took 36 milliliters. What is the molarity now that we are at 86 milliliters? Again, these have to be the same number. 0.108 times 50 divided by 86. You got your 0.0628. And then you got your 0.15 times your 36 divided by your 86. And you have your 0.0628, exactly the same number. All right, so equivalent point, they have to be exactly the same. One of them doesn't go to 0. Both of them at the equivalence point goes to 0. So you subtract the smaller number. They are the same number, 0.0628 minus 0.0628 plus 0.0628. So this is our initial. You have to have something 0 on the right. So we have a new initial. At the equivalence point, they are both 0. And we have our 0.0628 molar. All right, so we don't have a buffer because we don't have any concentration of HA. These are zeros. So now you have to do change and equilibrium. You can't have zeros, so you have to form an amount X on the right. So at equilibrium, 0.0628 minus X, X, and X. All right, so you have your X squared over your 0.0628 minus X, and that is equal to, again, you have to be aware of what reaction that you are using. This is the KB reaction, and so it's equal to your KB. We don't have a KB, we only have a KA. That's fine because we know that KA times KB is equal to KW. And so all we have to do is take KW divided by KA, and we have our KB. So 1 times 10 to the minus 14 divided by the KA, which was 1.3 times 10 to the minus 5. One times 10 to the minus 14 divided by 1.3 times 10 to the minus 5 gives us 7.7 times 10 to the minus 10. All right, when your K value is that low, the chances of needing to check X are essentially 0. You would have to have a ridiculously small initial concentration for that to not equal 1,000, but we will check. So you take your concentration of your base divided by the your equilibrium constant for your base. So you got your 0.0628 divided by 7.7 times 10 to the minus 10. And now you're in the millions. That's way more than 1,000. So that is much, much greater than 1,000. So it is much greater than 1,000. You do not have to check your x value. Your x1 is your answer. So you take your 7.7 times 10 to the minus 10 times 0.0628, and then you take the square root of that product, and you have 6.95 times 10 to the minus 6. So that is x. Again, you have to check what is x every single time. You have to make sure you're using the right k value. What reaction are you using? KB. You must use the KB constant. All right, when you solve for x, what is x equal to? You have to see that your x, when you solve for it, is your OH minus. All right, so your x value in this problem is the concentration of your OH minus. And so now we know that our OH minus concentration is 6.95 times 10 to the minus 6 molar. And so we can go to the POH. So the negative log of that is 5.16. All right, and we know that the pH plus the POH has to equal 14, so the pH is 8.84. All right, and so that is the answer to the actual homework problem. What is the pH at the equivalence point? And the answer is 8.84. All right, and so the next question says calculate the pH at the half equivalence point. And all you need to do there is know that your pH is equal to the pKa at the half equivalence point. So we already did the pKa, it was 4.89. So your pH is 4.89. All right, but what is the volume? So the volume at the equivalence point was 36.0 mils. And so the volume at the half equivalence point is half of that, and that is 18.0 mils. All right, so you will need to know this for your plot. You're pointing when you are going to do your graph. The point is going to be your 18 mils, and the pH will be 4.89. All right, so at the equivalence point, that was your 36.0 mils, so that's your point there. 36 mils is 8.84. All right, so then we said add 40 mils of your NaOH. So now we're going to add 40 mils of NaOH. This is going to go beyond our titration. So we have already completed the equivalence point. We are adding excess NaOH. All right, so we have to do MV is equal to MV. This time the concentration of your OH minus is going to be greater than your concentration of your HA. All right, so we have the same equation. So we have MV is equal to MV for the HA, MV is equal to MV for the OH minus. All right, so the acid every time 0.108. The volume we used was 50 mils. That's what's in the Erlenmeyer flask. I need to know the molarity now that the volume is 90 because I said after 40 mils NaOH. So 0.15 molar, we added 40 mils of that. What is the molarity now that the volume is 90? So we get our two molarities, 0.108 times 50 divided by 90. And that gives us a 0.06. OH minus 0.15 times 40 divided by 90 gives us a 0.06 repeating. All right, so that 6 just keeps repeating. All right, so the A minus is 0. All right, so that is when you need a new initial. Anytime you have two non-zero numbers on the right side of a Ka, a Kb, or a Kw, one of those, or in the case of the equivalence point, both of those will go to 0. All right, so this time the 0.0600 is the smaller number. And so our HA is going to 0. We passed the equivalence point, so we have extra OH minus, and that is 0.006, just a repeating 6. And here we have 0.0600. All right, we do not have a buffer because we have A minus, but we don't have any HA. HA is 0. All right, and so you would have to go to your equilibrium. All right, so we'd have to go minus X plus X plus X. But remember, when you have a starting concentration of a reactant and a starting concentration of a product, you always neglect your X, and that X1 is always your final answer. You never have to check it. All right, and so you have your initial change in equilibrium, and since the X has 0 effect, your initial concentration will be exactly the same as your equilibrium concentration. All right, and so since we just want the pH, and we already know our concentration of OH minus, because it is going to be the same as the initial concentration, because we have a starting concentration of a reactant and product, we go right to the POH, which is the negative log of your OH concentration. So the negative log of a 0.006 repeating is 2.18. All right, and so we don't want the POH, we want the pH, and so they have to add up to give 14, and so here your pH is 11.82. All right, and so that's when your volume is 40 mils. All right, so now we have all of our data points, and we can plot our graph. All right, always pH on the y-axis. The x-axis depends on what you're adding. This case, we added NaOH. Sometimes you'll be adding HCl. Sometimes you add the strong acid. All right, so that means that we started with an acid, which means we had a low pH. Then we added base. We hit our equivalence point. All right, and so here is our equivalence point. That's when we had our 36 mils. And this is our 8.84 pH at the equivalence point. We also have our halfway mark, which is our 18 mils. That is the pH at the half equivalence point, which is equal to your pKa. And that was 4.89. We added 10 mils. And we got 4.47 maybe, I can't remember exactly. And then our initial, when it was 0, we had a 2.93, I think it was. All right, and so if we're going to connect these like that, and then we went beyond it, we went to 40. All right, so where it hits the line here, come across, and that pH I have written right there and circled 11.82. All right, so once you have your data points, then you draw your graph. Your equivalence point is where you have the very sharp increase when you're adding NaOH, or the sharp decrease in pH if you're adding HCl. All right, so that's your volume that you calculated for the equivalence point. And then you go halfway, which is 18, and that pH is your pKa. And then whatever point you had. This one had 10, it was 4.47 if I remember right, and this one was 40, which was 11.82. I can see it, it's right there. All right, so it's not going to be drawn to scale. It's going to be drawn and labeled. This increase on the y-axis is not exact. I'm not going to give you graph paper to get it exact. So you just label your 5 data points. All right, so that will be the hardest question on the test. All right, let's do 1690. All right. 1690, what is pH at the equivalence point when 22 mils of 0.2 molar hydroxylamine? All right, so if you're not sure what hydroxylamine is, well, you look at the Ka and you won't find anything. You look up the Kb and it's listed. So your hydroxylamine is A minus. You know that because it is going to be listed as a Kb. 1.1 times 10 to the minus 8. Anytime you have a base listed with a Kb, that means it's a weak base. And I always use the generic A minus for my weak base. You can write out the whole compound if you want. All right, and so of this A minus, I use 22 mils of 0.2 molar. And then it's titrated with HCl. And so now I have HCl, strong acid, simply H plus, and I have 0.10 molar. And I want the pH at the equivalence point. All right, and so whenever I see pH at the equivalence point, MV over C is equal to MV over C. You got your acid on one side, you got your base on the other side. All right, and so your acid, you have 0.1 molar. We don't know what volume is required. That's what we're solving for. All right, so we have 0.10 molar. The volume of that we don't know. Over the coefficient of 1, your base was given as a 0.20 molar, and the volume of that was 22 mils. All right, so that's what's in your Erlenmeyer flask. Your HCl is what's in your burette. All right, and so when you solve for volume, you don't need your calculator for this one. It is 44 mils. You get your calculator, but you don't need it for this one. All right, so you would have to add 44 mils of your 0.1 molar HCl to reach the equivalence point. All right, so what we have is we have H plus and we have A minus. So we have H plus and we have A minus. There's only one reaction of the 3, Ka, the Kb, the Kw, that has both H plus and A minus in it. And that is your HA going to H plus and A minus. All right, so now we have to do MV is equal to MV. We really only have to do it once because we are at the equivalence point. By rule, it has to be exactly the same number. So your acid, 0.1. Volume, we just calculated 44 to reach the equivalence point. So what's the molarity now that the volume is 44 plus 22? That is 66. For your base, it was 0.2 molar. We used a volume of 22 mils. What's the molarity now that the volume is 66? Again, these numbers must be identical. So 0.1 times 44 divided by 66. And that is a 0.06 repeating. And when you take your 0.2 times your 22 divided by your 66, you also get a 0.06 repeating. All right, so again, at the equivalence point, those two are both going to 0. They have to be exactly the same number. All right, so when you subtract the smallest number, it doesn't have a smallest number. They are both the exact same number. One of them has to be 0. At the equivalence point, both of them will be 0. All right, and so there's your initial. Here is the new initial where both of your products are 0. So you have 0.06 repeating HA, 0 and 0. You don't have a buffer. There's no A minus. You don't have excess H plus. It is 0. You have to do the equilibrium to get your answer here. So minus x plus x plus x at equilibrium, your 0.06 repeating minus x and x. So x squared over your 0.06 repeating minus x is equal to, again, you got to look. What reaction are we doing? We are doing the Ka reaction. So you must have the Ka value. We don't have the Ka value. We only have the Kb. That's all right because we know Ka times Kb is Kw. So you simply take your Kw divided by the Kb. All right, so your Kw, 1 times 10 to the minus 14. Your Kb for the hydroxylamine was 1.1 times 10 to the minus 8. And so your Ka, so 1 times 10 to the minus 14 divided by 1.1 times 10 to the minus 8 is 9.1 times 10 to the minus 7. All right, so you got to check to see if your concentration of your acid initial over your Ka is greater than 1,000. All right, so you put in your 0.06 repeating divided by your 9.1 times 10 to the minus 7 and see what you get. 0.06 repeating divided by 9.1 times 10 to the minus 7. And that gives us 72,000. All right, so this is actually 73,000. 73,000, which is, of course, greater than 1,000. So you definitely do not need to check your x value. So you neglect your x, and you do not have to check that value. So 0.06 repeating times the 9.1 times 10 to the minus 7. Then you take the square root of that product, and you get a 2.46 times 10 to the minus 4. All right, so you have to, again, what is x? Well, you got to look. It's right here. It's right there. Your x is your concentration of H+. So now we know x is H+, so we know our concentration of H+ is equal to 2.46 times 10 to the minus 4 molar, and the pH is the negative log of that. So the negative log of that answer gives you a 3.61. All right, and so the pH at the equivalence point is 3.61. All right, so note the equivalence point here. A strong acid reacts with a weak base to form a weak acid. So anytime you have the equivalence point of a strong acid with a weak base, it's always going to be less than 7. Because you are always forming a weak acid. And in this case, the answer was 3.61. Note the last one that we just did. The pH at the equivalence point, as we show the graph here, was 8.84. That's because we had a strong base with a weak acid that formed a weak base. And so the pH for that one is always greater than 7. The only titration where the pH at the equivalence point is 7 is when you have a strong acid and a strong base, which produces just water, and that is when your pH is 7. All right, let's do number 92. All right, sodium benzoate. All right, so when I see sodium benzoate, I know sodium is a spectator ion. That is A minus. Feel free to write the whole thing. I'm going to write A minus. All right, consider a 50 ml sample of a 0.250 molar of this weak base. So I have 0.250 molar. I have 50 mils. All right, it's going to be titrated. I'm going to titrate that with HBr, which is a strong acid. So I'm going to write H+, 0.2 molar. All right, so here is the question. Calculate the pH of the solution, all right, before we added any H+. And so we want the pH of that. So pH initial. All right, after 50 mils HBr, all right, at the equivalence point, and then they, oh, no, okay. They don't put this one, I'll put in some free points at the half equivalence point. Easiest question on the test. And then after 75 mils. All right, and then they don't say to do it, but, and then show the graph. All right, so same as we did before, A, B, C, I added D, E, and I added F. And so I added two pretty simple things. One is just if you know that the pH is equal to pKa at the half equivalence point. And then graph. So are you able to put your volume and your pH on a graph? All right, so those two things should be very easy. The hard thing here is always at the equivalence point. All right, so initial, before any H plus is added, we just have A minus. And they do give us the Kb, so they give us the Kb. The Kb for sodium benzoate is 1.6 times 10 to the minus 10. Not sure why they gave that to us. Because if you look on the Ka chart, benzoic acid is also listed, 6.3 times 10 to the minus 5. All right, so both of those are given. You didn't have to calculate either one. Normally, you're going to have to do just like every other problem. You're going to be given one, and you calculate the other one. All right, so we just have A minus. So A minus plus H2O goes to HA plus OH minus. Again, you have your three reactions. When you only have A minus, you've got to write the Kb. And that is given as 1.6 times 10 to the minus 10. And the initial concentration is 0.250. All right, you might just want to say here that Ca or Cb, initial concentration of the base, divided by Kb, is greater than 1,000. All right, you don't actually have to push the buttons. When it's minus 10 on the bottom, it's plus 10 on the top. It's a huge number. It's way greater than 1,000. But you can actually get the number if you want to. The key is you have to show that you are giving X1 as your value because of this. All right, and so you have to go to the right. But that K value of minus 10 is extremely small, and so it is not going to change our initial concentration of 0.250. So initial, change, equilibrium. Again, we don't need a new initial because both of these are already zero. Only need one of them to be zero. In this case, both are zero. So we have 0.250 minus x, we have x, we have x. And so x squared over 0.250 minus x is equal to the Kb, 1.6 times 10 to the minus 10. You neglect this x, you do not have to check it. And so you take your 0.25 times 1.6 times 10 to the minus 10, and then you take the square root of that product, and you get 6.3 times 10 to the minus 6. Again, you have to know what x is. So you look at your equilibrium. X is your concentration of OH minus. So your OH minus is 6.3 times 10 to the minus 6 molar. And now you take the negative log of that to get your POH. And that gives you a 5.20. And then your pH, we know they have to add up to 14, so that is 8.80. All right, so your initial pH is 8.80. So now we're going to add some HBr. The pH is going to come down. All right, we're going to add 50 mils of our HBr. All right, so we're going to have 50 mils of 0.20 molar HBr added to our 50 mils of our 0.250 molar A minus. All right, so we have H plus. All right, HBr, strong acid, that's H plus. We have A minus, we need the reaction, and there's only one that has both H plus and A minus in it. And that is HA goes to H plus and A minus. And we will have to do MV is equal to MV. MV is equal to MV. They made the numbers very simple for this one. All right, for your acid, 0.2 molar. Volume is 50. All right, now I want the molarity now that the volume is 100. So when you add 50 mils to 50 mils, you simply cut your initial concentration in half. So this is 0.10 molar. Same thing for your A minus. A minus was 0.250. The volume was 50. What is the molarity now that the volume is 100? And that is half of the initial 0.125. All right, so you have your after mixing concentrations. HA is 0. We added 0 of the HA. So that is initial. That is not going to work because one of these is not 0. And so you need a new initial. The lower number goes to 0. The lower number is 0.10. So now we have 0.100 molar of our HA, and we have 0 of our H plus, and we have 0.025 molar of A minus. All right, and so you should be able to recognize that as a buffer. All right, when you have an initial concentration of HA and an initial concentration of A minus, remember the new initial, one of the products, your H plus or A minus for the Ka reaction or the Kb or the Kw, something on the right has to be 0. All right, and so you have your buffer. So once you have your buffer, you have pH is equal to your pKa plus the log A minus over HA. If you don't recognize the buffer and you go through the equilibrium, you get exactly the same answer. It's just a lot more work. All right, so the pKa, we have the Ka value. It was 6.3 times 10 to the minus 5. And so the negative log of 6.3 times 10 to the minus 5 is 4.20. And so your pKa is 4.20. So your pH is 4.20 plus the log of your A minus concentration, 0.025, over your HA concentration, 0.1. And that gives you a pH of 3.60. All right, so after 50 mils of your HBr is added, your pH is 3.60. All right. All right, so at the equivalence point. All right, so at the equivalence point, MV over C for your acid is equal to MV over C for your base. All right, so your HBr, 0.2 molar. What volume is required to reach the endpoint? That's what we're trying to find out. Your base, 0.250. The volume of the base, 50 mils. And so you take your 0.25 times your 50 divided by your 0.2, and you get 62.5. So the volume of your HBr required to reach the equivalence point is 62.5 milliliters. All right, so that could be a question all on its own. What volume of your HBr is required to reach the equivalence point? That is 62.5 milliliters. All right, and so we have our same reaction, HA, H plus, A minus. We have MV is equal to MV. We have MV is equal to MV. The only thing at the equivalence point that is easier is we know those two numbers have to be exactly the same. So your HBr, we had 0.20 molar with a volume of 62.5. What is the molarity now that it's mixed with the 50 mils of our A minus? And that gives us 112.5. So again, plus 50, that's your 112.5 milliliters. Your A minus, we had our 0.250 with a volume of 50. What is the molarity now that the volume is 112.5? Again, we're at the equivalence point. These have to give us the exact same number. All right, so this is 0.1 repeating. 0.25 times 50 divided by 112.5, and that is also 0.1 repeating. All right, so we didn't make any mistakes. All right, the equivalence point, they have to be exactly the same. All right, and so now we subtract the smaller number, the equivalence point, they are the exact same number. And so you subtract your .111 from both sides. All right. All right, and so you have your new initial, which you have your 0.1 repeating, and these are both zeros. All right, you have to look at the reaction. You have to use your Ka because that is the Ka reaction. And so that is your 6.3 times 10 to the minus 5. And then you have to check to see if your Ca over your Ka is greater than 1,000. So you have your 0.1 repeating divided by your 6.3 times 10 to the minus 5. And that gives you 1,800. So it is barely more than 1,000, but it is more than 1,000. So it is greater than 1,000. We do not have to check our X value. All right, and so you have your minus X plus X plus X. You have your 0.1 repeating minus X, X, and X. So X squared over 0.1 repeating minus X is equal to 6.3 times 10 to the minus 5. You can neglect your X. You do not have to check it. So your 0.1 repeating times 6.3 times 10 to the minus 5. And then you take the square root of that product, and that gives you a 0.002646. All right, so that is your X value. All right, I don't do sig figs till the end. I usually just leave it on the calculator, 0.002646. All right, so you got to look at your reaction, and your X value is your H plus concentration. And so X is equal to your H plus concentration. And so that is equal to 0.002646 molar. And we then take the negative log of that to get the pH. So the negative log of that answer gives you a 2.58 pH. All right, and then it said after 75 mils was added. So the same reaction, HA, equilibrium with H plus and A minus, and MV is equal to MV. We are past the equivalence point. MV is equal to MV. The equivalence point required 62.5. All right, and so our H plus, we had 0.2 molar of HBr. We added 75 mils. What is the molarity now that we are at 125 total volume? Our weak base, we had 0.25 molar. The volume was 50. What's the molarity now that we've added the 75 and our total is 125? Right, so the H plus 0.2 times 75 divided by 125, that's a 0.12. The A minus 0.25 times the 50 divided by the 125, and that is 0.1. All right, HA 0. All right, so again, that is initial. You must get a new initial because nothing on the right is 0. So the lower number in this case is your 0.10. So now you have your new initial where you have your 0.10 HA, your 0.020 molar for your H plus, and 0 for your A minus. So you do not have a buffer. You have a concentration of HA, but you do not have a concentration of A minus. All right, and so you're going to have to go to equilibrium. So minus X plus X plus X. All right, and then at equilibrium, you have your 0.10 minus X, your 0.020 plus X, and X. And remember, when you have an initial concentration of a reactant and an initial concentration of a product, X is always, you neglect your X, you don't have to check it, which means any minus X or plus X will have 0 effect, which means your equilibrium concentrations and your initial concentrations are exactly the same. And so you go right to your pH. We already have our concentration of H plus. It is 0.02. So the H plus concentration is 0.020. And so your pH is the negative log of your 0.02. 1.70 is your pH. All right, and then it says to graph it. All right, I'm not going to remember those numbers. Okay, so pH. All right, and this time I'm adding volume of H plus, or you could put HBr, which means that I'm going to start at a high pH, and then I'm going to reach the equilibrium, and then my titration curve is here. So here is my equivalence point, and that was the 62.5 mils, and that was the pH of, I don't remember. Then I can go here, and that is the 31.25. And this is your pH, which is equal to your pKa. And the Ka value was that. What is going on here? All right, so let's get our numbers. .20. No, yeah. Okay, the 2.58. The 4.20. 0.6. All right, I think that's 4.20. And then we did volume. 10 mils? That's right here in the problem. No, none have been added. 50 mils. So 50 mils were here. And we need a number for that. We did the initial. Okay, then we did after 75. So that's the one we just did. And the one we just did, 75 mils, that pH, 1.7. All right, so I need equivalence point, pH. I didn't write anything down. All right. 92, 50 mils. Okay, that was 3.6. So 3.6, 2.58. All right, so if I remember those correct, and then our initial pH was, I don't remember that one either. Okay. And finally, the initial pH, 8.8. So when 0, now we're up here at 8.80. All right, so again, as you're adding your HBr, the pH is going down. Also remember, so here is your equivalence point. Everything here to the initial, not at the initial, so the equivalence point is not a buffer, the initial is not a buffer, but everything in between is a buffer. And then all of this is excess, in this case, H plus, and if you're going the other way, so our other graph would look like that. And here's your equivalence point. And here's your initial. So anywhere between the equivalence point and the initial, this is your buffer. So you would use the Henderson-Hasselbalch equation. pH is equal to pKa plus log of A minus over HA. And anything beyond your equivalence point, you have, in this case, excess of your OH minus. And you go right to the POH once you do your subtraction. The other one goes to 0, you're going to have excess OH minus, get your POH. The other one goes to 0, you're going to have excess H plus, go to your pH. So this is the way those will look. All right. All right, 94, which is much, much, much easier. All right, although it's very easy and people miss it because, well, it's not as easy as you might think. All right, so calculate the pH. You have 35 mils of 0.15 molar acetic acid, which has a Ka, you look it up, 1.7 times 10 to the minus 5. And you have 27 mils of 0.1 molar of the acetate, A minus. All right, and so you see that you have a concentration of HA and A minus, so we have a buffer. So we know that we're going to use pH is equal to pKa plus the log of A minus over HA, and the reason people miss it is they put in the A minus of 0.1, they put in the HA of 0.15, and that is not the concentration. You have mixed these. And so you have to do MV is equal to MV for your HA. You have to do MV is equal to MV for your A minus. That is the concentration of your HA and your A minus in this buffer. It's not a buffer until you mix them together. So your HA is 0.15 with a volume of 35. Now its molarity is, well, we're going to calculate it, but the volume is 62 mils. So here our A minus was 0.1 with a volume of 27. What's the molarity now that the volume is 62. You have your 0.15 times 35 divided by 62, and that is a 0.0847. And then you have your 0.1 times 27 divided by 62, and that is your 0.0435. Now you have your correct concentrations. And so you have your pKa, which is the negative log of 1.7 times 10 to the minus 5. Which is a 4.77. All right, so now you have everything you need to find the pH. So you have your pH is equal to 4.77 plus the log of your A minus 0.0435 over your HA 0.0847. And that gives you a 4.48. All right, then the only problem that I actually didn't do, I will do that one, and that was the first one. For some reason, I skipped 1634, but just in case you have a question about 1634, it says, write the chemical equations for the acid ionization for each of the following. Express these in terms of H3O+. So if you have a specific question like these, HCO2H, plus H2O, when it says you have to have H3O+, then you have to add water. And then it doesn't matter what H you take off, but HCO2H. Organic is weird. It's actually, this is your acidic H, but again, you don't need to know that. Then your HF plus H2O, so either H that you take off is fine. Here you got your H3O plus and your F minus. So I say it doesn't matter, but if in the directions it says you need H3O plus, well, then you have to follow the directions. Normally it doesn't say that, but if it does, here is what you would write. And then your HOCN plus H2O. Again, remember, it's the same if you use H3O plus or if you simply use H plus. But those are the four answers for 34. So now I think I've done every single problem out of the book. So the test is tomorrow. You can come at 8:15. You can come at 12:30. You can come at 3:20. Any of those times is fine. And the lab is not due until next Thursday.